Okay, calculus fans, we are finally ready to talk about Taylor and Maclaurin series. Chapter 11 has been kind of a long one leading up to this, and now we're ready to put the pieces together. So, if you remember in the previous section, we were able to use geometric series to find power series representations for certain types of functions. Okay, those were functions that we could somehow manipulate to look something like that, right? We could use some sort of geometric series to get a power series representation. But we want to get more general. So now we're going to expand our capabilities to the more general problems. So suppose a function f can be represented as a power series. Then from section 11.8 we have this. F of x is equal to this, where this is our power series, which keeps on going forever, of course. So let's say we're going to work with this function right here. This is function y equals f of x. And let's first approximate it using a horizontal line. And we're going to approximate it at a particular point. So let's say we've got this point on the number line a, right? So this point up here, since this is y equals f of x, then this point right here on the curve is the point a, f of a. Okay, so if we were going to approximate this function using a horizontal line, which wouldn't be a great idea, but if we did, we could have this horizontal line shooting right across here. And, you know, this horizontal line would be the line y equals whatever that y coordinate is, right? So in this case, our line would be y equals f of a. And you can see if we're going to use this horizontal line to approximate this curve, it's only going to be good right at that one point, right? They agree at this point. That point is a f of a, and the curve y equals f of x and our horizontal line agree there. But as soon as you go away from a, errors develop immediately. So if we're going to do this using a horizontal line, that's what we would get. So this line is not very good. But the best we can do with a horizontal line. Okay, so we can definitely do better though, right? So we don't want to really do this. So instead, what if instead of this line, what if we took this line and we tilted it? So maybe we make it slope. In fact, what if we had it sloped in such a way that it was a tangent to this curve? Like maybe find the derivative of this function and have the slope of the line be equal to that derivative of the curve, right? So let's try that next. So let's approximate f of x using a polynomial p of degree 1. So if it's degree 1, of course it's going to be a line, right? Degree 1, so x will be raised to the first power, the first degree, right? With the same slope at a as the slope of the function at a. All right, so I draw a similar point A here. So here we are at point A. So we still got this point A, f of a. But this time, instead of having a horizontal line, we're going to have a line that's sloped. So now we're going to have this line that is tangent to the curve right there. So it's definitely a better approximation, right? So it agrees with the curve at that point, but now as you go away from A, the errors aren't quite as bad. I mean, it's still not great, but it's definitely better than this horizontal line. Okay, so what we've got here, so we're going to call this approximation, we're going to call it a polynomial p. So this curve right here, of course, the original curve is y equals f of x. And now this other curve we've got is y equals p of x. And it's our first degree polynomial approximation. It's just a straight line. And it has the same slope at a. So it has the same slope at this point a as f of x has at a. So basically what we've got here is this. We've got p of a equals f of a. So our line at point A is the same as the function at point A, and also the derivative is the same. So they have the same slope. And then we can do something with this because, if you remember from the good old days in algebra class, we have this form of an equation of a line, right? The point slope form. Got the point x1, y1 that's on the line. We've got the slope. So we can come up with the equation of this line just looking at this. So the point on the line is a f of a, so this is going to be x1, y1. And the slope, well, the slope of this line is just the derivative of the function at that point a, right? So we could say this is equal to y minus f of a is equal to the slope, which is f prime of a, times x minus x1, and x1 is just a. So now if I take this formula and solve this for y, so I'm going to add f of a to each side, we'll get y equals f of a plus f prime of a times x minus a. And that may look familiar. In Calc 1, you probably saw something like this, because in Calc 1, we call this a linear approximation. So this is in Calc 1, we said, hey, here's a linear approximation of the function. So it's a straight line that approximates that curve. Well, it was also, although it may not have been mentioned, but it's also called a first order Taylor series. So this linear approximation is a Taylor series. It's called first order because it means it's the first degree. It's going to have a 1 degree, so it's x to the first power. A second order Taylor series wouldn't be a line, it would be a parabola, right? It'd be a quadratic function. But this is a linear approximation. It's also a Taylor series for this line that we're using to approximate the curve. Okay, but what if we could improve this more? What if we could take this line and bend it up here on this end and bend it up here on this end? So we put a curve on it. We could do that if we had one more condition here. If not only the derivatives were equal, but the second derivatives were equal. Because if the second derivatives are equal, that means the concavity is equal, right? So that would kind of cause this line to curve around, and sort of wrap around this function. So it'd be a better approximation yet. And we could do that if we had a second degree function, a quadratic. So let's take a look at that. Okay, so we're going to approximate f of x using now a polynomial p of degree 2, which is as the graph will be a parabola, right? It'll be a quadratic function with the property that the value of p and the value of its first two derivatives match. Okay, so we're going one step further. So we've got p of a is f of a. We've got p prime of a is f prime of a. We've also got p double prime of a is f double prime of a. Okay, so what we've got here is the same sort of thing. We've got this point A here on the number line. This point on the curve, y equals f of x, that point is a point A, f of a. And now what we're going to have this line here, but it's going to bend around because we're going to end up having a second degree equation, or a parabola. So it would be something like, maybe this parabola that goes up like this, maybe comes around, goes something like this. So it's going to be even closer to the curve around here, right? It's a second degree equation. So what happens here is this, when the first derivatives are the same, that means they're going to have the same slope. When the second derivatives are the same, now they're going to have the same concavity. So it just causes this parabola to hug the curve a little bit better even. Okay, so what we want to do now is figure out how we can find this quadratic, how to figure out this quadratic. And then from there, see if we can express the function as a power series. Okay, so what we're going to do is do sort of what we did above here with the equation of a line, but it's going to be a little bit more work because it's a parabola, and we're going to make use of this right here. Okay, so let's see how we can do that. So to start off, we're going to think back to section 11.8 where we talked about a function that could be represented as a power series. So in other words, f of x is equal to c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared plus ... So this right here, this is our function f of x. Right, so if it can be represented as a power series, it would look like this, where this keeps on going forever, right, to infinity. But what we're going to do is we're going to find p of x. We're going to find p of x. This is going to be our polynomial approximation. So what we're going to do, we're going to have a second degree. So we're going to figure out how to express this as a second degree polynomial, which would be called the second order Taylor series. So we're going to approximate this f of x with this polynomial. This is going to be our second degree polynomial, and we're going to use this to approximate the actual curve. Okay, so this is going to be our polynomial approximation. To f of x. Now when we do this, we're looking for these coefficients. Now these are going to be the same coefficients here. We're just stopping here, whereas if this were really going to be equal to the function, they would keep going forever, right? But we're just going to find the first three of them, c sub 0, c sub 1, c sub 2. These are going to be the same. We're just going to stop here, and we're going to use this second degree equation to approximate this function. But in the process of this, we're going to be able to see a pattern that will allow us to find all of these constants, these c sub n's, right, all these constants. There'll be a pattern that emerges once you look for this. Okay, so to get started, here's what we need. This is what we said from the previous page. What we need is p of a to equal f of a. We want our polynomial to be the same as the function at point A. We want p prime of a to equal f prime of a. We also want p double prime of a to equal f double prime of a. So we want the second derivatives to equal also. So here's what we need. Okay, so to get started, we've got our polynomial p of x that we're going to use to approximate the function, and I need to find the derivative and the second derivative. So let's just start off by writing down p of x. And remember these c sub n, where n is just some integer. So c sub 0, c sub 1, and c sub 2, these are just numbers, right? These are just coefficients. So if I take the derivative, p prime of x, the derivative of any constant is just 0, so that's gone. The derivative of this, well, the variable is here, x minus a. So the derivative of x minus a is just 1. And then this is a constant that just goes along for the ride, so I'm going to get c sub 1 plus, and here we've got the power rule, right? So we're going to go 2 times c sub 2 times x minus a to the 1 power, right? So we'll get plus 2 c sub 2 times x minus a. And then to find the second derivative, p double prime of x, well, this is a constant, so that goes away. And the derivative of x minus a is just 1, so we just get 2 c sub 2. Okay, now remember our goal is to find these coefficients here. C sub 0, C sub 1, C sub 2, which is the same as these. So what I'm going to do now is figure out what is P of A, P prime of A, and P double prime of A just by plugging them in here. Okay, so P of A, P prime of A, and P double prime of A. So if I plug in A for X, this will go away, right? Because P of A P of A, if I put an A in for x, that is 0, that is 0. So I just get C sub 0. Likewise, over here, if I plug in an A for x, that ends up being A minus A, so that whole term is gone, so I just get C sub 1. And then the last one, there is no place to even plug this in, right? There is no x here, so this is just a constant always. So P double prime of anything is just 2C sub 2. You get 2C sub 2. And now we're going to make use of something here. If I look at this, P of A is C sub 0, right? Or C naught. And over here we know P of A equals F of A. So I'm going to use these two things here. And this will tell us that C sub 0, this thing we're looking for, is equal to F of A. Right, we're looking for this C sub 0 here and here. C sub 0 is P of A. Well, what's P of A? P of A is F of A. So C sub 0 is F of A. We can do something very similar here with this one and this one. P prime of A is C sub 1. But also P prime of A is F prime of A. So that means that using those two things, we can see that C sub 1 is going to be F prime of A. Okay, that is kind of ugly. Let me try that again. So that is going to equal F prime of A. And then finally, let's use this third one here. And with this third one, we'll use this third one. Okay, P double prime of A is 2, C sub 2. P double prime of A also is F double prime of A. So that implies that 2C sub 2 equals F double prime of A. Or in other words, C sub 2 is F double prime of A divided by 2. So now we know what these C sub n's are, right? C sub 0, C sub 1, C sub 2. All right, so what we can say then is this. All right, I could say, let's see the quadratic approximation. So the quadratic approximation, so f of x is approximately equal to, right? I'm using this to approximate the function. So the function is approximately equal to this thing here, because I'm only going to go out to the second degree, so I'm not going to say equal. So the function is approximately equal to P sub x, and that is equal to, let's see, C sub 0, which is F of A. It's equal to F of A plus C sub 1, which is F prime of A. C sub 1 times x minus A. Okay, and then we have plus C sub 2. C sub 2 is F double prime of A over 2. F double prime of A over 2 times x minus A squared. Okay, so what this is right here, this is a quadratic approximation. Which is also called a second order Taylor series. And if you look at it, isn't it just, here's the linear approximation, right? We had one more term to get the quadratic approximation. And that's how they work. If we want the cubic approximation, I've got one more term. But to find those terms, we want to see if we can find a pattern in here. So there's some invisible things here I'm going to fill in, and then you'll be able to see the pattern. Okay, so this is quadratic approximation, but I'm going to fill in things that are missing here. Okay, there's really a 0 factorial here times x minus a to the 0. There's a 1 factorial here times x minus a to the 1. There's a 2 factorial here times x minus a squared. So if you had to guess the third one, if you wanted to make a cubic approximation, we'd have to add one more term. So if I added one more term, I would say plus, you can see what's going to happen? F prime, F double prime, F triple prime, right? I'd have F triple prime of A over 3 factorial times x minus A cubed. You might not notice the factorial here, but 2 factorial is 2, right? Because 2 factorial is just 2 times 1. So it's 2 factorial here. So you can sort of see the pattern. So if I wanted to add another term, it'd be f to the 4th derivative, right? The 4th derivative of f at A divided by 4 factorial times x minus A to the 4th power, and so on and so forth. So the formula that we'll see then, the formula for the coefficient, we can say the general form. The general form for a coefficient in Taylor series is this. C sub n is equal to f to the nth derivative of A. Remember, once the derivatives go beyond 3, like if we had the 4th derivative, we put 4 in parentheses, okay, divided by n factorial. And this is what we see here, right, for the third one, and they would all just sort of repeat. Now we have to make this formula work everywhere, we just have to do something that might seem a little strange, but it sort of makes sense. We have to allow the 0th derivative of f to just be the function itself, which kind of makes sense anyway, right? The 0th derivative of a function is just the function itself, like we didn't take the derivative. So as long as we're willing to allow that notation, then we'll be able to use the notation that is on the next page for Taylor series. And you can sort of see what they're going to do. They're going to substitute this for each coefficient in the power series expansion. And then we get this. And so thus, we get to use your favorite word, thus. How many classes do you get to use this word on a daily basis? Not too many. Not too many. It's your lucky day. Speaking of lucky, did you see the size of this packet? This 11.10 packet is gigantic, which is why we'll probably cover this video in 2 parts. We'll do half of it with this video, and then we'll have a part 2, because this packet is just gigantic. So finally, if we have a function, or if a function has a power series representation at x equals a, and a is just some number, then this is how it, when all the details are in here, you can see all the patterns here, and it cleans up as this. So this is the one we'll typically use. So for Taylor series, we typically use this. F of x equals, and then we'll just use this here. Now remember, if I put the equals, I need to go to infinity. If I stop before infinity, it's not equals, it's approximately equals, right? It's an approximation. And this is the formula for the Taylor series. And what they say is the Taylor series of a function f at a, or about a, or centered at a. Because let's see, when we use Taylor series, we're going to center it at some point. And it'll start at that point and sort of wrap itself around the original function. The graph will. All right, so we're going to center it at some point A. Now, if A happens to be 0, like right at the origin, if A happens to be 0, then this will clean up a little. So all the A's will be zeros, and x minus A would just be x minus 0, which is just x. And when that happens, you have what's called the Maclaurin series. The Maclaurin series is just a special case of the Taylor series where A equals 0. So if A equals 0, then the previous information in that box above us just cleans up a little like this. And of course, when you get rid of all the little patterns here, you end up with this. So this one looks like f of x equals. This is the one we would typically use. And in this section, you'll write this out so many times, you'll have it memorized without even trying. And this is the Maclaurin series, which is just a Taylor series centered at 0, right? At x equals 0. And then I'll mention something that some of you will see. Let me just mention something while we're right here. There's Taylor series, and some of you will study Fourier series. So Fourier series, if you're going into electrical engineering, you'll probably study them for sure. But even mechanical, I think you'll study them. And some of you will even see them in differential equations. So they're kind of like what we're doing with Taylor series. Taylor series are said to be the best for approximating things locally. So like if you were going to try to approximate some crazy messed up function, maybe you can't integrate it, has no closed form solution, or you just want to approximate the function at some point, Taylor series are really good at wrapping itself around a function at a particular point. And it can be really accurate around that point. As you get further away from the point, you either need more terms or it just, the errors increase. So they're said to be the best locally. And Taylor series, as you know, these use polynomials, so they're really convenient. They're easy to use, and you'll see when we do more of these, differentiating and integrating is super easy with Taylor series. They're said to be the best locally. So if you need to estimate a function at a particular point, Taylor series are great. Fourier series are said to be the best globally. So Fourier series, they're used in telecommunications, in places where there are periodic signals. These are a little more, they're definitely more work. Okay, these use sines and cosines, and combinations of sines and cosine. And you can, they're said to be best globally because they can represent a function on a wide range of values. So you don't have to just like zoom in at a spot. And they can even like represent digital signals. So if you have like some sort of digital signal coming through, you can see like what they'll do is they'll still use sines and cosines, but they'll have these little sines and cosines, and they'll come up here. They have sines and cosines will come down here. So you can represent even digital signals with them. But so when you see them later, and many of you will see these later in a later class, they're sort of like Taylor series, same sort of idea. You're using them to approximate functions. So, okay, that's just something some of you will see later. But for us, we are ready to now use our find our first Maclaurin series for cosine of x and find its radius of convergence. So when we do this one for cosine, we're going to do one for sine also. You'll notice that sine and cosine, because it's something that's going to happen, we need to do a little bit more work than normal. So what I mean is, to do this, we start off with f of x equals cosine of x. And to do Taylor or Maclaurin, we typically take a few derivatives. So take the derivative, you take the second derivative, take the third derivative. A lot of times that's about all you need. But because of what's going to happen with cosine, we're going to have to go all the way down to the sixth derivative. Okay, so remember, once you get past the third derivative, we just use parentheses. Okay, and then what we're going to do, because it's a Maclaurin series, we're going to focus at x equals 0, right? It's Maclaurin series. So then we want to find f of 0, f prime of 0, f double prime of 0, and so on and so forth. F to the fourth of 0. Okay. Again, normally we don't have to go so far, but you're going to see what's going to happen with sine and cosine. It sort of forces us to. So what I do now is I just go down the list here and just start taking derivatives. So as long as you studied in Calc 1, you should be okay here. The derivative of cosine is negative sine. Derivative of sine is cosine, so the derivative of negative sine would be negative cosine. And then, of course, the derivative of negative cosine would be sine. And then we start over here. We've got cosine, negative sine, and negative cosine. Okay, now I need to take these functions, and plug in 0 for all of them. This is where a bunch of them are going to drop out, because wherever sine is, when you plug in a 0, you get a 0. So cosine of 0 is 1. Negative sine of 0, of course, is 0. You can just go right down here and plug all the signs are all going to be 0. Negative cosine of 0 is negative 1. Cosine of 0 is 1. Negative cosine is negative 1. Okay, so we have this. And now here's where, if we want to use Maclaurin, we do this. F of x is equal to, okay, from the previous page, f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed. And I'm going to go a little further than normal because, as like I talked about, there's a whole bunch of them that cancel out, right? So let's go f to the 4th of 0 over 4 factorial times x to the 4th plus f to the 5th of 0 over 5 factorial x to the 5th plus dot, dot, dot. Okay, so let's see if we can figure this out. So cosine of x then, cosine of x is equal to f of 0, which is 1, plus f prime of 0. Well, f prime of 0 is 0. In fact, you can see f prime of 0 is 0. F triple prime of 0 is 0. So if this is 0, it's going to wipe out this whole term. And basically all the odd powers, right? The odd powers of the derivatives are all going to be 0. So that's going to be gone. That's going to be gone. So what we'll have is this one, f double prime 0 is minus 1. So I'm going to get minus x squared over 2 factorial. And then I get plus f to the 4th is there. F to the 4th, that's going to be 1. So it's going to be 1 times x to the 4th over 4 factorial. And then we got f to the 6th. I ran out of room here, but you can see I would have had f, the 6th derivative at 0 over 6 factorial times x to the 6th. So if I just fill that one in, I get minus x to the 6th over 6 factorial, and then plus dot, dot, dot. Okay. And this is called the expanded form. Now in practice, when you're doing applied problems, usually the expanded form is what you're going to use, because we'll just list out a few terms here. And if we have to integrate or something, we'll just list out a few terms and start doing the integration. Notice also cosine. If you remember, just looking at the graph of the cosine function, it's an even function, right? Like y equals x squared. It's even because it can be reflected about the line, about the y-axis. So even functions can be reflected about the line, about the y-axis, right? So it's an even function, and that's also shown here in the polynomial approximation. These are all evens, right? X squared, x to the 4th, x to the 6th. This would be like x to the 0. So cosine function, it's an even function, and it's also shown to be even here when you expand it. So that's the expanded form. Once we have this, there's another way, another form here that is also used, especially in our book. They'll use it quite a bit. And that's just using sigma notation. So if I look at this, what we've got here, you see if we can come up with a pattern. So first, notice that it's definitely an alternating series, right? It's an alternating series here. So I'm going to have, let's see, negative 1 to the n. And then notice that I've got all even numbers down here, even numbers and their factorials. So if my inputs are integers and I need to make them even, how could I do it? Well, I could double them all, right? I could just say this is going to be 2n factorial. Now make sure you don't say 2n factorial. That's completely different, right? These are completely different things. Not equal at all. So we need to double the input and then put a factorial, right? So when this is 1, it becomes 2 factorial. When it's 2, it's 4 factorial. 3, it's 6 factorial, like here. And then the powers are the same way. It's going to be x to the 2n. So this is equivalent to this, because if I plug in a 0, I'm going to get negative 1 to the 0, which is 1. 0 factorial, which is 1 by definition, right? So it's 1 over 1. And I'll get x to the 0, which is 1. So there's the 1. Then I let n be 1. Plug in a 1 here. I'm going to get a minus 2 factorial, and then x squared, right? You plug in a 2, you'll get here. So these are equivalent. This one is just called sigma notation. This is using sigma notation. Okay, so there's the expanded form of cosine of x, and there's the sigma notation of cosine of x. They're exactly the same. Okay, and then the question asks us to find the radius of convergence. So let's try it out. Let's find the radius of convergence. So this will be like what we did in section 11.8, right? The radius of convergence. So we have to use the ratio test. So use the ratio test. Remember in 11.8 they were finding the interval of convergence and the radius of convergence. So what we do is we use the ratio test. We basically take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. We've got this form right here, so we can use this sigma notation. So a sub n plus 1, if I fill this in, we get the limit as n approaches infinity. That's going to be negative 1 to the n plus 1 times x. Now I have to be careful here. I have x to the 2n. If this n becomes n plus 1, that's going to be x to the 2n plus 1, right? Which is x to the 2n plus 2. You have to be careful about that. I don't just make this 2n plus 1. I actually swap out n with n plus 1. So it's 2n plus 2. Right, so this is going to be 2n plus 2. Very similarly on the bottom, 2n factorial becomes 2n plus 2 factorial, right? Because this n gets swapped out with n plus 1, so I get 2 times n plus 1, which is 2n plus 2. Okay, then we divide by a sub n, which is like multiplying by the reciprocal, which would be 2n factorial, negative 1 to the n times x to the 2n. All right, let me get rid of some of this stuff. Okay, then all right, so looking at this, well, I'm not going to worry about the negative ones, okay? They're going to cancel no matter what because they're in the absolute value, so I don't need to think about, well, n plus 1 minus n doesn't even matter. They're in absolute value, they're going away. So what about x to the 2n plus 2 divided by x to the 2n? Well, that'd be 2n plus 2 minus 2n, right? Which would just be x to the 2, x squared. So that's gone. This is just x squared. And now 2n plus 2 factorial, what that means is 2n plus 2. And then I subtract 1 and keep multiplying. 2n plus 2 minus 1 is 2n plus 1. So I subtract 1 and keep multiplying. This is 2n. Then I could just say factorial, right? So you just keep taking 1 away. And you'll be 2n factorial, which is what we've got right here. So that is what we wrote right here. And now we can cancel 2n factorial here. So now what we get is the limit as n approaches infinity, x squared. I guess I don't really need to put that in absolute value, but it's not going to really matter anyway because you can see what's going to happen when we take the limit. Right, so the only thing left up here is the x squared, and down here we've got this. Now when we take the limit, it doesn't matter what x is. X could be 7, could be 1,000,000, could be 4. It doesn't matter. This denominator is going to get huge, right? As n goes to infinity, this denominator is going to infinity. So I have some number I could plug in here divided by infinity, basically. This is going to get as close to infinity as we want. So the limiting value of this is going to be 0, which is less than 1 for all x, which means the radius of convergence is infinity. It converges everywhere. Interval of convergence is negative infinity to infinity. Okay, so to answer their question, the radius of convergence is infinity. So it doesn't matter where we're working. If we're integrating cosine x between -4 and 10, nothing matters. Between 0 and pi over 6, it converges everywhere, so we don't have to worry about it. But just to see how this works, what I want to do is I'm just going to use these first 4 terms of cosine, just these first 4. And I want to try something. I want to plug in cosine of 0.1. I want to plug this into the calculator, so using the quartic algorithm that our calculator uses. And we'll see what the calculator gets. And then also, I'm going to use this. I'm going to just punch this into the calculator and see what it gives. So just 4 terms. Now, to do this though, it'll be much easier if I just store 0.1 in for x, and then I can just punch it in just like this. So on your calculator, you have there's a little key in the lower left side that says, it just looks like this. It looks like STO, like that. So to use this, it'll store a number into a variable location. So I'm just going to put 0.1 stores in, then I'm going to hit the X key. And once you do that, it's going to store 0.1 in X. Then I can just type this in just like this. Okay, so when you do that, the factorial key, 2 factorial is just 2. So you're going to see when I type it in the calculator, I'm just going to put 2 here, because 2 factorial is 2 times 1. 4 factorial is 4 times 3 times 2 times 1, which is 24, but I'm going to put the 4 factorial in here. So to get to the factorial key, you just press the math menu and you scroll over to PRB, probability. So math, probability, and then it's like the 4th one down is the factorial. So that's how you get there. So I'm going to type this in, have the calculator calculate it. And I probably have mentioned before, the calculator uses an algorithm. The Texas Instruments, I believe Hewlett-Packard, and I think Casio also, they use something called the quartic algorithm. TI does for sure, and the other 2 I think do. But they use, it's just an approximation technique. It's going to get an answer. And then I'm going to punch this in just like this after I store 0.1 in for x. Of course, you don't have to. You could just put 0.1 squared, 0.1 to the 4th, 0.1 to the 6th. That works just fine too. But I want to see what we get. Okay, so you can see what happened here. I used 0.1 and I hit stores in x. 0.1 stores in x. So it stored it in there. Then I just typed this in just like it was. So this is the first 4 terms of that approximation. And you can see, even with only 4 terms, it agrees with cosine of 0.1, right? So it works fairly well. It converges pretty quickly. Now remember, 0.1 is fairly close to 0, so that's why. I mean, these numbers, if we went further out, there would be disagreement, right? Because this is centered at 0, and this is a little bit away from 0. But if we wanted to be more accurate, we just add more terms, right? So it's pretty good for 4 terms. And to see why, I think what I'm going to do next, I'm going to graph this expression and also graph cosine of x. And then I'm going to hit zoom trig. So it will put the window into like a nice trig window, a trig viewing window. So if you want to try it out, just put maybe put this in for y1 and put cosine of x in for y2 and then graph them. So I'm going to do it a second and see what we get. Okay, so I graph those. You can see the cosine graph right here, right? This cosine graph. And this one comes up and it hugs the graph really well right around the origin, right? It's like about from here to here, it's really close, then it drops down. So if I wanted to get better, I just add more terms. And if I add more terms, this would curve back up, right? And it will just, you can make it as close to cosine as you want just by adding more terms. But I want to now move to something a little further out. So I'm going to hit cosine of pi over 4. I'm going to do the same thing. I'm going to ask the calculator what cosine of pi over 4 is. And then I'm going to store I'm going to store pi over 4 in for x and then type out that last command and see what it does. Okay, so if you look at what happened, I stored pi fourths in x, and then I brought up the last command here. Remember how you can do that? You can hit second enter, and it will cycle through the previous commands. Now the newer software, I think you can just hit the up arrow and scroll through, but for the older versions, you just keep hitting second enter and it brought that back up, so I just hit enter again, so I didn't have to retype everything. So this is the answer I got, but then if I just ask the calculator cosine of pi over 4, I get this answer. So there's some disagreement here, because now, remember when we use Maclaurin series, we're centered at 0, and now we're getting further away from 0 over at pi over 4. So there's going to be some errors that start to develop, so it's not as accurate. So if I wanted to tighten up on the errors, there's two things we could do. We could just add more terms, that would work. Or instead of using Maclaurin centered at 0, we could use Taylor series and just slide along the x-axis. So maybe center it at pi over 4 or center it closer to pi over 4. Okay, so remember Maclaurin is centered at 0. In Taylor series, we can center it anywhere at x equals a, where a can be any number. Okay, so hopefully that is making sense. You'll start to see some of the usefulness of Taylor and Maclaurin. This example 2 here, as soon as I put this example up in this paper, I was thinking this is not really a great example. What would happen is we would do pretty much the same thing we just did for cosine of x. And what I was going to do is show you that way and then show you the easy way, which is down here, ask us the same thing. But instead of just going through that long way again, I'm just going to show you the easy way. So once we have a formula for cosine of x, it's pretty easy to change it to cosine of 3x or really change any of the inputs. So we've got, remember for cosine of x, we've got two versions of cosine of x. We've got the expanded version. We've also got the sigma notation, and I'll show you how to use both of them to change this. Okay, so let's say we've got cosine of x, and I'll use the expanded version first. So cosine of x we know is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus ... Okay, so if I wanted cosine of 3x, here's how easy this is. Cosine of 3x, wherever I see an x, I put 3x. So it's going to be 1 minus 3x squared over 2 factorial plus 3x to the 4th over 4 factorial plus 3x to the 6 over 6 factorial. Oh, wait a second. That's a minus, isn't it? Okay, let's get rid of that plus. That's a minus there. And then plus ... So if we wanted to clean that up, we could just say, okay, this is equal to 1 minus... I guess we could just go 3 squared x squared over 2 factorial plus 3 to the 4th x to the 4th over 4 factorial minus 3 to the 6 x to the 6 over 6 factorial plus ... Okay, so that's doing it with the expanded form. And if we do the sigma notation, well, let's start with cosine of x, which is n equals 0 to infinity of negative 1 to the n, 2n factorial times x to the 2n. So then cosine of 3x is just going to be n equals 0 to infinity, negative 1 to the n, 2n factorial. Instead of x, we've got 3x to the 2n. Well, we know that a times b to the n is just a to the n times b to the n. So that means that Cosine of 3x is equal to n equals 0 to infinity, negative 1 to the n, 2n factorial times 3 to the 2n x to the 2n. Sometimes what people will do is they'll want to put the variable part out in front. So you might see something like this instead. You'll see n equals 0 to infinity, negative 1 to the n, 3 to the 2n, so that'll be on top, over 2n factorial, then out here will be x to the 2n. Okay, so they're really the same. And you can see also, if I wanted this part, well, you would get it if you just started filling in 0, right, and kicking these terms out, you would get this. So like if I plug in a 0 here, negative 1 to the 0 is 1, 3 to the 0 is 1, so I get 1 up here. 2 to the 2 times 0 is 0 factorial. 0 factorial is defined to be 1, so this is 1 times x to 0, which gives us 1. Okay, then I plug a 1 in here. Negative 1 to the 1 is a negative, so I get a minus. 3 to the 2 times 1, which is 3 squared. 2 times 1 factorial, which is 2 factorial. X to the 2 times 1, which is x squared. All right, so they're the same. This is just expanded form, and this is using sigma notation. So then if you have maybe instead of 3x, cosine of x cubed, it's just the same. So once you get cosine, you can do all kinds of variations of it really easily, right? Using either method, expanded or sigma notation. So if we've got, I don't know, let's just start off. Let's just use our sigma notation. N equals 0 to infinity, negative 1 to the n, 2n factorial x to the 2n. So then cosine of x cubed, wherever I see an x, I'm going to put an x cubed, right? So it's 0 to infinity, negative 1 to the n, 2 to the n factorial, x to the 2n. Well, if I have x cubed to the 2n, that's just x to the 6n. All right, pretty easy. So sigma notation looks like that. And if you want to do the same thing with expanded form, well, we know cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus dot, dot, dot. Then cosine of x cubed is going to be equal to 1 minus, well, x cubed squared is x to the 6, right? Plus x cubed to the 4th, x to the 12th, right? Because I basically have x cubed to the 4th, right? That would be x cubed to the 4th, which would be x to the 12th. Then we have x cubed to the 6th, so there'd be a 6 here. That's going to be x to the 18th. X to the 18th over 6 factorial. Oh, I keep putting a plus there, don't I? I want to keep putting a plus. It's going to be a minus. So we'll go minus this, then plus dot, dot, dot. So we've got sigma. If we're starting with sigma notation, we get this. If we're starting with expanded form, we get this. But they're the same, right? These are the same. If you plug in 0 here, negative 1 to the 0 is 1. 2 times 0 is 0 factorial, which is 1, and you get x to the 0, which is 1. So you just get 1. If I plug in a 2 here, I'm going to get plug in a 1. I go from 0, then 1. Plug in a 1, I'm going to get a minus. 2 times 1 is 2 factorial, and x to the 6 times 1 is x to the 6, and then you keep on going, right? So they're the same, just different ways of doing it. Different ways of writing the expression. And then we've got one more, and then I think we will call it the halfway point. We'll take a little break. So the last one, we want to find the Maclaurin series for sine of x. So remember, Maclaurin series, that means we're going to center this at x equals 0, right? We're going to center it at x equals 0. So we're going to do this for sine of x. Sine and cosine are similar in that they take more work than most because of all of the terms that are going to cancel out. So just like before, we just start off with sine of x. And we need to go down the road, down the line here. Normally, as I said, you only need like maybe the third derivative, but special cases like sine and cosine, you need a lot of them because half of them are going to cancel out when you plug in a 0. We want to be able to see the pattern. Okay, so then we're going to, because it's Maclaurin, we're going to plug in 0 for all of these and see what we get. All right, so we're going to get cosine minus sine minus cosine, sine, cosine, minus sine. Okay, then we plug in zeros for all the inputs. All the signs are going to be 0. We'll do those first. So we get a 1 here, a -1 here, and a 1 here. All right, so let's see. We know f of x is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed plus f to the 4th of 0 over 4 factorial times x to the 4th plus dot, dot, dot. Okay, so that means sine of x is equal to f of 0, which is 0. Now we're going to see all the even ones go away. F of 0, f to the, even powers of the derivatives. So the second derivative, fourth derivative, sixth derivative, they all go away. So f of 0 is gone. Second derivative, that's 0. That's 0. So we're going to have the fifth derivative here. Be able to just add this one in so we can see it. So after this, of course, there was plus f to the 5th of 0 over 5 factorial times x to the 5th. So then sine of x is going to be equal to f prime of 0 is 1, so we're going to get 1x, right? F prime of 0 is 1, so it'll be 1x or just x. Then we've got triple prime is -1, so we get negative x cubed over 3 factorial minus x cubed over 3 factorial. The fifth derivative at 0 is 1, so this is going to be 1 times x to the 5th over 5 factorial. And I'm sure you can see at this time the pattern is going to be minus x to the 7th over 7 factorial plus dot, dot, dot. Okay, so this, again, this is expanded form. And you can see that the sine function is an odd function. So think of the graph of the sine function. It goes like this, right? It's an odd function. Odd functions have the property that if you rotate them 180 degrees, they're said to be symmetrical with respect to the origin. So you spin them around 180 degrees and they repeat. So odd functions like y equals x cubed or sine. And you notice that sine is built of all odd-powered functions, right? The opposite of cosine. Now, if we wanted to write this in sigma notation, well, we can see it's alternating series again, just like cosine was. But now, instead of evens, we've got odds. When we had an even down here, we went 2n and then factorial, but now we've got an odd. So for all the inputs that come in, what we can do is make them even by multiplying by 2 and then either adding or subtracting 1. In this case, to make this work, we just add 1. So it's going to be 2n plus 1 factorial times x to the 2n plus 1. And that is sigma notation for the sine function. And these are equivalent, of course. You start plugging in 0, 1, 2, you'll get this will come out. And so those are the two forms for the sine function. And then one thing you can take a look at, there are some very common and important Maclaurin series in the book. There's a little box in the book. So there's some common series. Common Maclaurin Series. In the 9th edition, it's on page 804. That's in the 9th edition. And the 8th edition, it is on page 768. You'll find sine and cosine there and some other pretty common ones. But that's probably a good spot, good breaking point, good halfway mark. So why don't you try the homework in section 11.10. Some of the stuff we haven't talked about yet. So if you're working on a homework problem and it doesn't make sense, just hold off on that one and go on to the next one. And we will finish this up. There's just a lot of material. It's important material. So I want us to take our time and take 2 days on section 11.10. So try the homework. Try the ones that we've covered that make sense. And let me know if you have any questions, and we'll finish this one next time.